Okay, so this is a video I'm recording to help people with section 3.1 in the David Lippman textbook. So a couple of things that come up in this section is what's a power function? So if I have f of x equals x, well, actually we can put a coefficient in front of it, and I'm going to have some exponent there. This is a power function, and it can have different terms. It only needs to have one term, but can have many different terms. And I know this is a power function because I got a variable that's being raised to a power. So that's what makes a power function versus if I have, no, let me not use e because I don't know if you know e. If I have 2 raised to the x, see here how I have a number being raised to a variable. This is an exponential function, and we'll study those later. And this is not a power function. Okay, so when you look at that, if you see a number raised to a power or a variable, that's not a power function. So a power function it'll have coefficients. Could be just 1. It could be negative. They'll usually be real numbers. We won't usually see something written like a plus 3i raised times x squared. I mean, that's a complex number. We don't usually see them written that way. So they're well behaved. They're nice, neat polynomials is what we're talking about. And some things you probably know from earlier on is from earlier coursework that if I have a function that has an even power, like f of x equals x squared, or f of x equals x to the 4th, those are going to end up looking like this. If I have my xy axis, and let me change ink color here, it'll look something, both of them will look something like this. Now, there could be some things going on in the middle, but in the long run, they end up going up to positive infinity. So, and that brings up the next piece. How do you describe the ending behavior? So, the ending behavior would look like this. You'll say, as x goes to negative infinity, y would go to positive infinity. And then as x goes out to positive infinity, y also goes out to positive infinity. And that's when I have one of these even looking functions, even exponents. And actually x squared is an even function, right? Because remember, if we plug in f of negative x, the negatives cancel off, we'll get x squared. So that is an even function, same thing with x to the 4th. I got to be careful with that, because what happens when I ask you something like y or f of x equals 3x to the 4th plus 7x cubed minus 2x minus 1. Well, notice I'm missing an x squared term. That isn't what really matters. What really matters is I go out to infinity, that largest exponent is the one that's going to rule. So if I were to zoom way out on a graphing calculator, there'd be a bunch of stuff going on in here, and I don't know what's going on without looking at it. But I do know that the same ending behavior would hold. I mean, if I zoomed out far enough, I wouldn't see any of the stuff happening around the x-axis. I'd only see where it's happening on going out to infinity. Okay, so make note of this arrow notation in ending behavior. I'm going to ask you this on an exam, and it'll help you in calculus too. Okay, so I think that's good. I guess we should do some definitions. Okay, so what we need to worry about is what's a coefficient? Well, if you look at a polynomial, actually it doesn't have to be a polynomial. It can be any kind of a function, but since we're dealing with power functions, that's what I'll stick with. So if I write 3x squared plus 2x minus 1, I'm seeing a coefficient of 3, that's the number in front of the variable, and that has a coefficient of 2. And this actually, the negative 1 is actually a coefficient, because I think of this as negative 1 times x to the 0. So the negative 1 is also a coefficient. Often, though, we'll talk about this as being the constant term, because it doesn't change regardless of what x is. Okay, so that would actually be the better way to think about it. So that's the constant term. We have to talk about the leading coefficient and the leading term. Oh, maybe we should talk about the degree before we get there. Oh, what's a term even? So each one of these is a term. And I know this is stuff you probably did in Algebra 1. So I have three terms in this trinomial because there's three terms to it. And the one term is 3x squared, the next term is 2x, and the constant term is -1. The degree is the biggest x, or the exponent. So in this term, the degree is 2, and this term, the degree is 1, and this term, the degree is 0, because it's just x to the 0, which is 1. The leading term is the term with the largest exponent. So in this polynomial, the x squared is a leading term, the x squared term is a leading term, and the leading coefficient is the 3. And so how does that help us? Well, if we know we have f of x equals negative x to the 4th minus 3, or plus 3x squared minus x minus 1, I know that I know the leading coefficient on this is negatives. That tells me it's been reflected. This function's been reflected around the x-axis. I'm thinking about that work we did in chapter 1. Okay, so what's going to happen is I don't know what's happening around there. I'd have to do a little more analysis on this, and we'll do some of that. But for now, all we really care about is what's happening with the ending behavior. And I know, because it's a 4th degree equation, both curves are going to be, both sides of this polynomial are going to head in the same direction. But because of the negative in front of it, it's going to be headed to negative infinity. So in this case, I would say the ending behavior as, I was going to do some calculus here. Excuse me for a minute here. Let me erase this. So as x approaches negative infinity, I'm seeing that y goes to here. Where's my as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y also approaches positive and negative infinity. And I know this because that leading coefficient has a negative, is negative. That leading coefficient is less than 0. So let's finish this. So as x approaches negative infinity, y also approaches negative infinity. As x approaches positive infinity, let's make an infinity sign, y also approaches negative infinity. Okay, so that's for when it's an even. The leading term has an even exponent. Now, what happens if I have y equals I don't know, 30x to the 3rd minus 7x squared plus 2x minus 100. I'm just guessing, making this up. So I see my leading term has a positive coefficient of 30. It has the degree of this polynomial is 3, because that's the largest exponent. Another textbooks, you might find its order degree. The degree of the polynomial is 3. This is a 3rd order polynomial. Sometimes you'll see that. I won't usually talk about that. So everything else way out infinity. So what I want you to think about is all out infinity, that negative 100 doesn't matter. Neither does the linear term, neither does the parabola term, the quadratic term. That x cubed term rules everything else. So I don't know what's happening around the origin or around the x-axis, but I do know, because this is a positive leading coefficient and the degree is 3, the function's going to look like this if I zoomed way out. So in that case, if I wanted to talk about my arrow notation and talk about the ending behavior, as x goes out to negative infinity, y will head to negative infinity, and y as x approaches positive infinity, y also approaches positive infinity. And we can see that on the graph, because it heads to negative infinity, heads to positive infinity. So that's how we deal with all that. Ending behavior, long run behavior is the same idea. Okay, then comes the tricky part. And actually, it's not too tricky yet. What we need to do is this. Let me stop this and I'll come back for a minute. So here's a function. I know that this is a 3rd degree. This is the 3rd degree equation. I know that because if I were to expand all this out, it would be negative 2x to the 3rd with a bunch of other terms. Okay, so that's one how, and then we could talk about the long run behavior, right? We could talk about how, well, let's see, the leading coefficient's negative. So whatever's happening around the x-axis, we don't really care about that right yet. I do know that it's going to end up looking like this because this is the cubic functions have been reflected around the x-axis because of that negative leading coefficient, right? So so that's that part. Now, what I wanted to do with this was what's the short run behavior? What is happening around the x-axis and the y-axis, and because that can be important too, especially when trying to make a rough sketch about what's happening. So what's nice about this equation that I gave you is it's all factored out. We don't have to do a lot of work. But if I'm looking for the x-intercepts, I want you to think about what is the y-coordinate at all these points on the x-axis. Well, I know x is, I don't know, what if this were -3? X equals -3. And what if this were +2? And what if this were x equals +3? What would be the y-coordinate for each of those points? I hope you're thinking 0, because everything along the x-axis is the y-coordinate of 0. So that's why they call it x-intercepts. And if we needed to solve this equation, what we're going to do is we're going to say, hey, when does y equal 0? And of course, you've done this before. This is not new material for you. Might not remember it, but I know you've done it. So what I got to ask myself when it's in factored form, I got to ask myself, well, when does x minus 3 equal 0? Well, if you think about the algebra, I'm going to add 3 to both sides, and I get 3. But I'm hoping that you guys just see, oh, what minus 3 is 0? 3. So 3 is an x-intercept. What plus 3 is 0? Well, you know that x equals -3 is an x-intercept. And what minus 2 is 0? Well, you know that x equals 2 is an x-intercept. So my open math, and if on a test I ask you what are the coordinates of the x-intercepts, you'll need to write 3, 0, -3, 0, and +2, 0. Okay, make sure you include the y coordinate being 0. If I don't make that specification, but I don't say what are the coordinates, you can just say x equals. So that's that part. Now, what about the y intercept? Well, let's see here. Let me go to a different. Let me do a little erasing here. And what I'm going to do for the y-intercept is you want to think about, well, let's see. I said that the x-intercepts were 0. So what are, no, I don't want to do that. I want a pen. There we go. What are all the x-coordinates on the y-axis? Well, I'm hoping you realize that it's going to be 0 and some y value, right? So what we're doing is we're going to substitute. We're going to find what's f of 0, and that's how I'm going to get my y-intercepts. So -2 times 0. I'll write this out, but I'm hoping you don't write this out ever. I mean, you get enough to do without having to do all this writing. So it's negative. Now, this is what I would love to see. -2 times -3 times 3 times -2. And that's going to be my y-intercept. And so what is that? There's going to be 4 times 9. -9 is -36. So the y-intercept is 0, -36. And if we had to graph that, well, so if I had to graph this, and this is a rough sketch, and part of getting ready for calculus to be able to do rough sketches. Let me come back to black ink here. So I'm going to make my XY axis, and this certainly is going to be the scale because I don't want to have to graph -36. But I do know it crosses the x-axis at -3. I do know it crosses the x-axis at +2. I know it crosses the x-axis at 3. And I know it crosses the y-axis way down here at -36. And then I know this is a third-degree equation. So, and I know that it's reflected around the x-axis. So I know the long-run behavior will look like this. So all I got to do is get it to match. I got to put a curve through these points and match that ending behavior. So I'm going to come down I'm going to come down like this. I'm going to pass through that. I'm going to come down to that y-intercept. I'm going to come up. I know it's got to go up above because I know in the end it's got to go heading down like this. Okay, and I don't have that exact, but what we're doing here is we've got the general. See, I've got the ending behavior. I think on paper I would have done this a little better. Let me get my eraser going. Whoops, I didn't want to do that. Undo. I want this part here to be a little more smooth. I didn't do that. I would, if I were to do that again without having to erase everything, I'd probably make it come down something like this. Because these are supposed to be nice smooth curves. All right, so that brings up the last thing I need to talk about is turning points. How do I know how many turning points a function, a polynomial or power function can have? Well, I'm seeing just by graphing at this that there's 2 turning points. And I know this is a 3rd degree equation because I have to FOIL that out, multiply that all out, expand it, as we say. It's going to be a, it'll be a 3rd degree, will be the biggest degree, will be the degree of this equation, this polynomial. So I know and I see there's 2 turning points. So at most, there's always going to be n minus 1 turning point. So where n is the degree. That doesn't mean there will be, but it means there could be. Because if you consider, let's see, turning points. So what if I have just x cubed? If I have x cubed, there's only going to be this one little squiggle. There's going to be this one little squiggle, and really that's not a turning point. It's something like a turning point, but it's not. I've seen some books call this a vertex. I don't know if I like that either, but I know it is this kind of critical value that's in x cubed functions. Okay, but that's that. So all this rule, this how many turning points, you always want to word it as you can have at the most well, whatever, n minus. So if I have a 4th degree equation, I know there's going to be, if x equals to the 4th plus 7x to the 3rd minus 2x squared minus x plus 10. I know there's going to be 3 turning points in that because it's n minus 1. Well, I mean, it could be only 3. 2 turning points, but I know at most there'll be 3 turning points. Okay, so that's pretty easy. Take the degree and do the turning points. Now the only other thing is, what if I give you a graph? Let's do that. Okay, so then we've got these graphs. I'm sorry, it's a little distorted, but I want to blow it up enough so that you guys could see it. You folks could see it. So I'm seeing 2 turning points here. I'm seeing a turning point here, a turning point there. So that tells me that would have to be. And I'm also noticing, so the other thing I'm seeing ending behavior that looks like an x cubed. Okay, but I know it can't be, well, I know it shouldn't be an x cubed. I have to be careful here. I know because the ending behaviors, it should be x cubed. It could also be x to the 3rd. There's some things that I'm seeing here, though. It's kind of makes me think it's going to be just an x cubed. I'm seeing 2 turning points. So if you think about 3 minus 1 is 2, that's telling me at most an x cubed could have 2 turning points. That's what I'm seeing. I'm also only seeing 1, 2, 3 zeros, and then as you learned in Algebra 2 or college algebra, if you're a college student watching this, the degree, the fundamental theorem of Algebra 2 tells us the degree will tell us how many zeros there are. So I'm only seeing 3 zeros. I'm seeing 2 turning points. I think the least possible degree, actually, I think the degree for this would be x cubed, would be 3. Okay, and this one, I'm seeing 1, 2, 3 turning points. I'm only seeing 2 zeros there, right? So this brings up another quandary. It must be, because if this were 3 turning points and we use that n minus 1 trick, but I'm seeing 3 turning points, that tells me it has to be a 4th degree equation. So it must be something's happening with these 2 zeros. It must be 2 non-real zeros, 2 complex zeros in the mix. And we'll have to learn how to discover that. I know you did some in Algebra 2, but we'll have to explore that a little deeper here in pre-calc. Okay, so we talked about zeros, we talked about turning points, we talked about leading terms, leading coefficients, the degree, what a term is, and then that arrow long run behavior, that ending behavior. So hopefully this is enough to get you going with the bookwork and get going with it. And then if you want, there's some open math on the same stuff.